Have you ever wondered why the exact same program runs at drastically different speeds on different computers? The code is identical, yet it finishes in 1 second on someone else's machine while taking over 10 seconds on yours. Is it insufficient RAM? Or an outdated CPU? Today, we're uncovering the secrets behind this. From CPU architecture and cache hierarchy to instruction pipelining, let's explore how computers make the same program run at different speeds. Many people think CPU speed is all about clock speed, that 3.0 GHz is faster than 2.5 GHz, much like assuming a car with a larger engine always goes faster. But that understanding became outdated over a decade ago. Here's an analogy. A sports car with a top speed of 200 km per hour can only carry one passenger at a time, while a truck with a top speed of 150 km per hour can carry 20 people. To transport 100 people, the sports car would need to make 100 trips. While the truck only needs 5 trips, the truck ends up being faster overall. It's the same with CPUs. Clock speed reflects single operation speed, but factors like architectural efficiency, instructions per cycle, and cache hit rates also determine actual performance. In CPU terms, there's a concept called instruction issue width, which refers to the number of tasks processed at once. Early Intel Pentium 4 CPUs, despite reaching out to 3.8 GHz, used a single issue architecture. They could only execute one instruction per clock cycle. Modern CPUs like Intel's 13th Gen Core or AMD Ryzen processors, however, use a 4-issue or even 8-issue architecture, capable of executing 4 or 8 instructions simultaneously per cycle. So, at the same clock speed, a modern CPU can process 4 times as many instructions per second. Early CPUs could only execute one complete instruction at a time. Each instruction had to fully finish before the next could begin. Modern CPUs, however, use instruction pipeline. A single CPU cycle is divided into stages: fetch, decode, execute, and write back. The CPU can handle different stages of multiple instructions at the same time. The result is a dramatic increase in execution efficiency. However, pipelining has a weakness. When a branch misprediction occurs, such as when the program encounters an if-else statement, the CPU predicts whether the if or else path will be taken and preloads the corresponding instructions into the pipeline. If the prediction is wrong, all instructions in the pipeline must be discarded, and the correct instructions must be loaded from scratch. The entire pipeline has to be flushed and restarted. You may have heard the saying, a computer's speed isn't about the CPU, it's about the cache. CPUs are incredibly fast, but they spend most of their time waiting for data because they have to fetch it from RAM. And RAM is hundreds of times slower than the CPU. That's why modern CPUs include multiple layers of cache memory: L1, L2, and L3. L1 is closest to the CPU core, smallest in capacity, and fastest. It stores the instructions and data the CPU needs immediately, like the code in a loop or the variables used within it. L2 is larger but slightly slower, storing data likely to be needed soon, such as function parameters called later in the loop. L3 is the largest and slowest, shared among all cores as a data warehouse, holding core sections of the entire program. Ideally, you'd want all your data on the L1 cache for the fastest access. But the space is limited. So, if a program's data is frequently accessed, the CPU keeps it in the cache. The higher the cache hit rate, the better the performance. When data isn't in the cache, a cache miss, the CPU sits idle, waiting for the data to arrive. Thus, a program's speed also depends heavily on its cache hit rate. Digging deeper, why does the same program compiled and run on different CPUs yield different results? This comes down to differences in the instruction set architecture, the language the CPU understands. Different CPUs speak different languages, so they handle the same program with varying efficiency. x86, ARM, and RISC-V each have their own execution methods. Mainstream ISAs fall into 2 categories: complex instruction set computer and reduced instruction set computer. x86 is a classic example of CISC, while ARM and RISC-V are typical RISC architectures. CISC is characterized by one instruction doing multiple things. For example, an x86 instruction can directly add data from memory to a register and store the result back to memory, accomplishing 3 actions in one instruction. The advantage is that the compiled program uses fewer instructions. An addition operation might need just one x86 instruction. But the downside is clear. Complex instructions require more complex hardware circuits to decode and execute slower. A single complex instruction might take 3 to 5 clock cycles. Also, variable instruction lengths complicate pipeline design, increasing the likelihood of branch mispredictions. RISC, in contrast, follows the principle of one instruction, one action. For example, an ARM instruction can only add the contents of registers R1 and R2, storing the result in RO. If memory data is involved, you must first load it into a register using an LDR instruction, perform the operation, and then store it back with a STR instruction, requiring 3 instructions for one addition. The benefit here is faster instruction decoding. Most RISC instructions are fixed length, simplifying hardware design, and often execute in one clock cycle. They also fit better into pipelines, reducing errors. As a result, the same C++ program, when compiled for different architectures, will differ in the number of instructions executed, cache utilization, and branch prediction performance. This explains why the same program can perform so differently on laptops, phones, and servers. Modern CPUs have two more performance-boosting tricks: superscalar architecture and out-of-order execution. Superscalar architectures allow the CPU to execute multiple instructions per cycle. For instance, a 4-issue CPU can fetch 4 instructions, decode 4 instructions, and execute 4 instructions each cycle, like 4 pipelines working in parallel. Of course, this requires that these instructions be independent. If 2 instructions depend on each other, they can't execute simultaneously. This is where out-of-order execution comes in. The CPU analyzes the dependency relationships among a batch of instructions. If it encounters a dependent instruction, it skips ahead to execute subsequent independent instructions first, then circles back to handle the dependent one once its dependencies are resolved. This allows the CPU to work around bottlenecks and keep busy. The result is maximized utilization of time and a significant boost in overall efficiency. By now, you should understand the same program running at different speeds is far more complex than whose computer is more expensive. It's the combined effect of the CPU's architectural design, cache size, pipeline depth, and instruction set type. All these hardware design choices collectively determine why the same program runs at different speeds on different computers. This is the fascinating world of computer architecture. On the surface, the program is the same, but underneath, the underlying realities are worlds apart.